Let's review the idea of energy that we studied in General Physics 1. Imagine that we have a system, right? In this case, the system is going to be this rocket. So what is the energy of this system? Well, the energy, as we remember for General Physics 1, is what? Is the kinetic energy, 1 half mv squared, where m is the mass of the rocket and v is the velocity of the whole rocket, plus whatever gravitational potential energy is there. So we are going to add a thermal energy component, right? E thermal. What is that component? What is that energy? Well, imagine the system is made up of these atoms, and these atoms are vibrating about this position here. That vibration is energy, okay, because they are moving. That is what we are going to call our thermal energy. So a system now is going to have a mechanical energy component, which is given by this, plus a thermal energy. And the change of energy, as we remember from General Physics 1, is what? Is the change in mechanical energy plus whatever thermal energy change there is. And that has to be equal to the work done on the system. This is what we remember from General Physics 1. If there's no work done, then the energy, if there's no external work done, the total energy of the system doesn't change. And that is your conservation of energy. So how do we change the energy of a system? Well, we need to transfer energy on the system, and we can do to the into the system. We need to transfer energy into the system, and we can do that in two ways. We can do work. So imagine that we have this box, and there is a tension pulling up, and this box is moving at a constant speed. So this tension is doing work because the box is moving, right? Remember, work is the tension times the displacement h. So if this box moves a distance h, this is the work done by this tension. So that is the amount of energy that is going into the box. Where is that energy going? Well, that whole energy, because the velocity is not changing, is not going into the kinetic energy, is going into the gravitational potential energy. So whatever work this tension is doing is becoming gravitational potential energy. Imagine the second case now. Sorry, another case in which we transfer energy by work. So imagine that now we have a box, and that box is in in contact with this surface here, and there's friction. And imagine again that the box is moving at a constant speed, so you're pulling here. So you're pulling again, so if this box moves a distance d, then there is work done, there is external work done by the box, which is T times D. So where is that energy? This much energy is being transferred into the box. Where is that energy going? In this case, the kinetic energy is not changing. The gravitational potential energy is not changing. So, but the system is heating up because there is a friction here, and that friction is heating up the system. So all this uh, external work being done by the tension is being transferred into thermal energy. So therefore, we can transfer energy to the system in two ways. By work, by doing work, and work is energy transfer in a mechanical interaction, or by thermal interaction. Energy can also be transferred between the system and the environment if they have a thermal interaction. So the energy transferred by a thermal interaction is called heat. That is what we are going to call heat. And the symbol for heat is going to be Q. And so the equation now from General Physics 1 can, tells us that the change in energy of the system is equal to the change in mechanical energy plus the change in thermal energy, which is W plus Q. So imagine a steady force that is pushing a piston, right? And there is insulation here. This is like a thermal, so there's no heat And so in this process, the temperature of the gas, what happens to the temperature? Increases, stays the same, decreases, or there's not enough information. Think about this problem and we'll come back to the solution. But let's just look at one more summary. So what I'm telling you here is this. So here we have an ideal gas, right? This is an ideal gas in this box. So what is the energy of this ideal gas? Well, the energy of this ideal gas is just the kinetic energy of the particle. There's no gravitational potential energy in this case, so we are going to ignore that. And there is no other type of energy, only kinetic energy. So we can write that the total energy of this ideal gas is 1 half mv squared, the sum over all the particles, right? So this is the total energy. So imagine that I want to change the energy of this ideal gas, which is my system. How do I do that? I can do that in two ways. I can do work. I have done work, right? I have pushed and done work, right? And or I can add heat, right? So these are the two ways in which I can change the energy of the system. We write that the change of energy of this ideal gas is equal to the work done on the gas, right? By compressing it like that, plus the heat that was added to the gas. So the gas can also release energy. So it can release energy. We can cool it down here, for instance, right there. I'm cooling down the gas. So heat is being released, so the energy is being changed. Or the gas can expand. If the gas expand, it's releasing energy. You can see now the particles are moving slower. If the gas releases heat, also releases energy, and you can see that the particles are moving slower. So we can go back now to our question, and so we have a steady force pushing on this gas here, right? In this process, the temperature of the gas, there is a gas here, when you push, increases, stays the same, decreases, or if there is no information. Well, there is no heat going in because there is insulation here. This is an adiabatic process. But work is being done, right? Because, well, there is a force and there is a displacement. So there is force times displacement, right? So this is the work done, which is force times the displacement. This is how much work is done. So so that means that there is that much energy going into the system. So the system increases by that much energy. Okay, and therefore the temperature increases.